of two different media, however, it remains in the same medium from which it was traversing. So you would have experienced those two concepts: reflection, where it bends, stays in the same medium, whereas with refraction, it bends, but it crosses over the boundary, moves from one medium to the next. Diffraction now is a slightly different concept. In this case, it is still the bending of light. However, this bending occurs when it interacts with a space or some interfering. One second, let me let in these persons. Give me 1 second. So, my apology. So when the light meet upon an opening or a spacing, once the spacing is smaller than the wavelength of the light itself, what will end up happening is that the light will bend and you will get a pattern that is formed. Because as it bends, what happens is it forms sub-wavelets, and these sub-wavelets will interfere with each other and create a pattern. If it is just one opening that the light goes through, it bends and creates a wavelets which interfere, and what you get is a diffraction pattern. The diffraction pattern you can observe by placing a screen. So what that means, what it then has is that you will have a series of light and dark regions, just like the band. You remember when you were doing the acceleration due to gravity and you were looking at the picket fence? Mr. Chin, I know it's too early for you to be yawning like that, right? The picket, you remember when you looked at the picket fence, it had these areas of clear and dark. Well, for the pattern, it has something looking like that, where you have bands where you have light being that you can observe, sorry, and then you have regions, alternating regions of darkness, right? However, for the diffraction pattern, what you will find is that there will be a central fringe, and that central fringe will be extremely bright, and then all other bright fringes will have lower intensities, and subsequently lower and lower intensities as they get away from that central fringe. So that central fringe will have, and when I say fringe, it means an area of between two edges, right? So it's whether it's an area of lightness or an area of darkness. That central fringe is bright and it has an area of lightness, right? And that is the brightest that you would observe in a diffraction pattern, and then that fringe will get smaller as well as less intense as you move away from that central one. The dark on either side of it will also fall within edges that get progressively smaller as you move away from that central one, right? So that's a diffraction pattern. So that occurs when you only have one slit. Now, in the event that you have more than one apertures, slits, holes, and those sort of stuff, you will have the lights also passing through them, bending, creating sub-wavelets, but these sub-wavelets will interfere to give you an interference pattern. So you get a diffraction pattern when it is just one slit. Once you have two or more openings, you're gonna get what is called a diffraction pattern. And the difference between the diffraction pattern and the interference pattern, as I told you, with the diffraction pattern, you have bright, and then progressively as you move away, it gets less bright, and the width or the thickness of these bright areas will get smaller. For the interference pattern, the bright fringes or the regions of brightness have the same amount of intensity as well as the same width, right? So they look more like the picket fence than the diffraction pattern would do. And the darkness regions are similarly in terms of they have the same width, and well, there's only one intensity for darkness. Let me let in. Oh, she got the message, Miss Rary. So she's here. So thank you for that. Okay, So we're good with the differences between the diffraction pattern and the interference pattern so far. We understand that the difference between diffraction of light and all other bending concepts where light is concerned. Because diffraction is, yes, a concept of bending. However, this occurs once it is that the light is attempting to pass through an aperture. And give me 1 second, let me welcome Miss Dixon. So Miss Dixon, welcome to today's session. My apology, when I saw your email, I was not able to respond at the time. And as a result, I couldn't inform you of today's session. But luckily, Miss Rary is also here. So she will be, so that's why she was able to send you the message. And I'm going to actually put both of you to work together for today. All right? Okay. So as I was saying, with the other concepts, though, those would have been where light meets upon a boundary or a medium, a boundary between two different media. So those would have been reflection, refraction. Today only is diffraction. All right. So with single slits, you get a diffraction pattern. With two or more slits, you have an interference pattern. Now, the amount by which the light bends depends on the wavelength of the light. So if the wavelength increases, in other words, the frequency is smaller, then what will happen is that the degree of bending will be larger, right? So that relationship is what we have in front of us. Now the relationship isn't direct between the amount of bending, and in this case, how we measure the amount of bending is to use the angle through which it bends, and it's the angle that it forms from the incident, the line along which it was incident to the fringe area itself, right? So that is the amount, and the fringe area is the area where the light, you observe the light itself. So the amount of bending depends on the wavelength. As I was saying to you though, it's not a direct relationship between the angle of bending and the wavelength itself. The direct relationship occurs between sine of the angle and the wavelength itself. So when you reach the concept, Mr. Simpson will tell you that the relationship between the sine of the angle of bending, which really is just an operation done on the angle. The relationship between the angle and the wavelength will be given by, well, d sine theta m lambda, right? Where d is the width of the spacing, and usually it is for the interference pattern to be nicely observed, you assume that the width of the spacings, remember I told the interference pattern comes from you having two or more spacings, or two or more slits, or two or more apertures. The width of these apertures should be consistent, they should be the same, right? And for you to be able to observe a very good sharp interference pattern. The M is the order, and then what is exactly the order? The order is the number associated with the fringe. Give me 1 second, ladies and gentlemen. My apology, the rain is falling. I have to lock up the windows. Give me a second. Alright, sorry about that. My apology. So as I was saying, the order is simply the position that the fringe has, and that whether it is the light fringe or the dark fringe, the position it has on either side of that central bright fringe. So the very first fringe which you find on either side of the bright central bright fringe would have an order of 1, right? And then the second bright fringe that you would observe, or the second band of light that you would observe, would have an order of 2. Same for the dark. The first fringe of darkness, or the first band of darkness on either side of the central bright one, would have an order of 1, right? So, however, when you're actually using the equation, you refer to the dark regions considering it as half rather than order of 1. So it would be the order plus half. All right. With the central one, though, you do keep it as having the order as is, which is whether 1, 2, 3, right? So it's a whole number. Okay, so are we fine so far that I can, is that enough background for you for us to be able to evaluate our experiment or exercise for today? Is there anything that you don't quite understand that I need to clarify or explain? Okay. Seems like we're fine. So moving on then, remember for our experiments or our exercises, for our sessions rather together, we're doing it slightly different. So it will be as usual, me just spending, not as usual, but me spending a few minutes just going through enough background, and then I would put you to work with someone, put you in your breakout room. You would then go through starting the report generation itself, and then of course if you need any assistance you would call me in and I'd come and assist you. The whole intent or aim hopefully is that by the end of the 2-hour 50-minute session you should reach far enough in your report generating that you're able to just spend a few more minutes or an hour the most later just to fine-tune for submission. I have done reconsideration based on some of your requests, and I will continue to leave it as Friday 11:59 p.m. So even though you should reach far enough in it, you still will get until, well, I appreciate all those appreciations. So I see Mr. Milan, I see who is this blocking? Mr. Thomas, Mr. C. Thomas. So I appreciate the appreciation. So we'll keep it as that. So let's go ahead and talk about this particular exercise. So in this one, you'll be using, well, they used, and you will be evaluating their use of the diffraction grating. Now, the diffraction grating is simply a device which has a number of slits, a number of apertures. Well, they use slits for theirs rather than apertures. So it has a number of slits, and these slits are usually in the order, some of them are in the order of 300. You have some which have 6,000 slits. So you have different numbers, but there are no small numbers such as 10 or 20. They're usually very high, second order, or even 10 to the third order, right? So these devices now, once it is that you shine light on them, what would happen is that you would have diffraction, but you would have these very, very tiny wavelets that will come out, and they will interfere in a number of ways, and then you'll be able to generate from these an interference pattern. And because of the sizing of the slits, these interference patterns are very sharp and nicely observable. Right? And once it is that the light is not diffuse, it's well focused, then you should get an interference pattern that you can readily observe. Now, because the bending of the light also depends on the wavelength, if the incident light that you're shining on the diffraction grating itself, it has a number of wavelengths within, what will happen is that these wavelengths will bend by different amounts. I remember when I say wavelengths, I'm talking associated within light. within the visible portion of the electromagnetic spectrum, remember that the different wavelengths are associated with different colors. And you have all the colors of your rainbow, RGBs, as we learned when we were in grade 2. So we would have learned about the red, the orange, the yellow, the green, the blue, the indigo, and the violet, right? All those different colors have their different wavelengths, and even within each color, you have bands within that color which have different degrees and therefore different wavelengths. So if the incident light or the light that you're shining in onto the grating has different wavelengths, i.e., that is different colors, then what you will find is that within the interference band, you will be able, within the light fringe of the interference pattern, you will be able to observe the different colors within that particular band. Right? So for the first order, you will see the light not as the yellow, as the color that it was incident, but with as the different colors that make up the incident light itself. Right? So you will see regions of light bands, which are your fringes, your light fringes in the different orders. But instead of using one uniform color, in that case, you will see the light in the different colors, right? So that's what the diffraction grating facilitates. So you need to be able to view it, right? So yes, you send the light through. Can you easily view it? Well, not necessarily if you don't put a screen. If you put a screen, you can see the pattern. Or you can use other viewing devices. And in this case, it's the telescope that allows you to be able to see the different colors and the different angles with which the light is bent, right? The different wavelengths are bent through. So this is Mr. Simpson provided you here in your handout, and I will have to apologize. You would have gotten the handout on Monday, which is when I would have retrieved it, and so I would have fixed it and sent it to you on that day. So you should have had access to it, and hopefully, though it's just 2 days ago, you would have had enough time to do some amount of background reading so that even as you haven't met the topic before, what I'm saying doesn't sound odd or unfamiliar. So either way, it's in this case, what would have happened? You would have had the light source. In this case, it says it's a mercury lamp, which they did use in the experiment itself. And then that would have been shone into the device, that the total complete device that you would be using to be able to collect the light as well as observe the pattern, the interference pattern. So remember, this is a diffraction grating. The pattern will be the interference one, not the diffraction pattern. It consists of first a collimator, which is that collects the light and allows it to be you to focus the light. Focus it on the device that you want to send the light to. Whether it is that it's a diffraction grating, which in this case it is, whether the device is a transparent material, a mirror, whatever it is, it collects it and allows you to be able to focus on that device. For our particular experiment, the device is a diffraction grating, otherwise called a transmission grating, right? So it has a number of slits. Then this device is put on a table. This table is rotatable, right? So that it can be turned, which would facilitate you being able to put the light in at different angles. Now, usually what you would do though is send the light in at an angle perpendicular to the surface of the particular device through which you want the light to which you want to focus the light, right? So you would have put that prism table at 90, such that it's at 90 degrees. How would you know? The top of the prism table has a protractor. Second yawn, Mr. Chin. And I don't know why I keep seeing you when you do it. So this table has a protractor on it, which allows you to be able to read off the different angles. The angle with which the incident light is to the device itself, as well as the angle through which the different lights get bent. So you're able to use it in that fashion. Right? You also have involved in this entire complete setup called the spectrometer telescope. Now, this telescope is what would allow you to be able to view the outgoing light, right? And so once you rotate the telescope to the different angles, you would be able to, once you reach the appropriate angle, view the particular light or the particular wavelength. And how you would know what the particular wavelength is depends on the color that you're observing, right? So that's the setup, but this is what the actual, yes, Mr. Tom.
No, not Mr. Tom.
Oh, wait.
Morgan.
Let me move this out of my way so I can see everyone. All right, go ahead. Let's see who spoke.
All right. So the wavelength that you're seeing is dependent on the angle, right?
Well, the angle that it gets bent to depends on the wavelength.
Okay. It's all the way around. Right. But if you're moving the
telescope,
right?
Mm-hmm.
Then wouldn't it become dependent on the angle, the wavelength that you would see through the telescope?
The light's already gone to wherever it needs to go, right? Is you moving the telescope so that you can see where it has gone.
Oh, okay.
All right. So it's just for viewing purposes. The light has done whatever it needs to do. It has bent as it needs to have bent, and it has settled into its new position. And you just move the telescope to go view where it is. All right. So here is the entire spectrometer concept, right? So here is the collimator. You notice it has a focus knob that allows you to sharpen the beam or have it more diffuse depending on what you're actually, the particular experiment that you're conducting. However, in this case, because it is you're trying to observe a diffraction pattern, interference pattern, you would want a more sharp or more focused beam, right? You also have the holder for in this case, because you're going to use a grating, you would use a grating holder. The grating that is usually extremely slim. It's almost like a thin sheet it's not quite, it's quite thinner than a sheet of glass. It's an extremely, like a thin sheet of plastic, right? It's not necessarily a plastic in material, it can be glass in material. I'm just telling you in terms of the thickness. So imagine an extremely thin sheet of plastic, and that's what the grating would look like. The lines are so fine that a lot of times you're not even able to identify them. Sometimes you may see them as scratches, but for the most part, they're so fine that because they don't necessarily cross the entire sheeting as well, sometimes you're not even able to see them, right? Also, as a result, a grating holder is sometimes put on top of the table. If you are using, like, for instance, a glass block or a mirror, the grating holder would have been removed. So it's easily removable. You just simply unscrew it and you can see the screws in there. And then that would allow you to be able to mount the other devices on it. But in this case, the grating holder is mounted on it so that you can be able to put the grating in. And then you would have had all these different screws that allows you to adjust the height of the table itself, whether you can rotate the table or lock it in position. So this screw allows you to lock the table in position so you can rotate it. So once you rotate it and you put it to a particular angle that you want the incident light on, you don't want any shifting of it. So sometimes what you will do is tighten the screw and keep so that it doesn't get to rotate, right? And then you have the different other screws that allow you to adjust the height of the table as well. Now you have the telescope on this end, which you will now rotate to be able to view, and that rotation is independent of the table's rotation. This rotation is total, and it can be locked in position. So if you want to see that you move the telescope to view the particular wavelength, and say you want to move away to write it down and you don't want any shifting to occur in the body to accidentally hit into it and turn it, you can have it also has screws that allow you to lock it in position. Right? So what you would do is you would turn the telescope.
Excuse me, please.
Yes, Mr. Thomas.
Miss, someone is asked to be let in.
Okay, thank you. And number two, second, I've managed to use my writing device. But we always prepare that have extra. Okay. All right, sorry about that. So right. So you can lock it into position. So this is your spectrometer, which would facilitate you being able to observe the interference pattern. If you wanted to see the entire pattern as it is, without having to go to the like you want to see everything one time, what you would do is instead of putting the telescope there, you would have put a screen, and then you just adjust the screen to the particular distance so that you can be able to see the different things. So let's move on because I already see some board faces that indicate that you're gearing and rearing to go started on your report writing. So let's talk about what it is that you would be analyzing or evaluating for today. So for them, they would have, as you see, put the collimator at a 90 first at the 90-degree angle to the surface of the grating, and then they would have now adjusted, turned on the light, of course, and then adjusted the telescope to the different angles so that they would have and looked at different colors. So this is what the different colors are for this particular mercury lamp. And this is group 10 information that I'm looking at now. I remember I'll put you with a partner, I'll give you a group number, and then the data that you evaluate will be associated with your group number. I will also put you in a room that has the same number as your group number. And so you, in the event you forget, the room number is the same as your group number. So this one has three different light colors, well, four really. It has violet, it has blue green, it has green, and finally it has yellow. But it has, remember, each color has different wavelengths as well because it's a band of colors. So it's a band of violet with different violets within that have different wavelengths. In this case, they have three violets in there, right? You have the one that is moderate in strength, one weak in strength, and one strong in strength. In terms of strength, we're talking about the intensity of viewing, right? And also it has the blue-green, which is slightly weak. That means it's usually more difficult to identify, but it is there. And the green and the yellows are strong, so they're very, very sharp. We are able to look at them and easily identify them. So they provided you with the wavelengths of these colors, and you will notice that you are now given the different angles. Now, for the first order, you would have noticed that you have two angles provided to you. Remember, the orders are on either side of the central bright fringe. So you have an order one that is on the left of the central bright fringe, and there's another order one that's on the right of the central bright fringe. Similarly, for order two, you will have um, fringes on either side of it, on the left and on the right. So they would have provided you here with the different orders, right? And the different on the different sides. For the first order notice, that means you will have to rearrange this table, and as a matter of fact, you'll be producing two different tables because you'll be producing two different graphs. You will now be evaluating based on the equation above, and I'm going back to it. You will be evaluating the relationship between the angle through which light is bent and the wavelength. So in that case, you will have options, and let me go ahead and put up the screen. You will have options of, remember the equation is m lambda is equal to d sine theta. So therefore, you can draw lambda going to be equal to d over m sine theta as one option, or you would have sine theta is equal to m over d times lambda. You can choose to draw a graph to show the relationship between wavelength and angle by either drawing one of wavelength versus sine theta, right, or sine theta versus the wavelength. The gradient, therefore, will be different depending on which one of them you choose to draw. Right. Now, the thing is, the gradient is supposed to be a constant, and as you see, you have two variables in this case, and you have one constant, which the constant is composed of the spacing as well as the order. The spacing is the width of the slit, and the order is the particular fringe number that you observe on this either side of the central fringe, the central bright fringe, right? So, in that case, for the first order, clearly m will be 1. Now, if this relationship is true, in the sense that the wavelength is proportional directly to sine of theta, then you should be able to use the gradient to be able to get information about the spacing. You should be able to calculate the spacing value from the gradient, right? Whichever one of them you draw, if the relationship is true. So if you draw your graph and you get a straight line relationship, right, a linear positive relationship, and that linear positive relationship demonstrates total proportionality, then you know and that your the relationship is true and proportional. If it is that when you use the gradient and use it to get your spacing value, you find that it is close to the true value, then you know that the equation is correct, right? So you will be using this information to be able to generate. Now you notice that you have different angles. Sine theta is unitless. So please do not give me anything where you have sine theta / degrees, right? Now you are going to have to generate two graphs, one for the first order, one for the second order, which means that you'll have to generate a table with data for the first order, and then you will give me the graph that's associated with it and then the subsequent calculations on it. And then you'll generate a table with information for the second order with the associated graph and calculations thereafter, right? For this, clearly,
sorry to interrupt. You said sine theta is in units length?
Yes, unitless. Unitless. Has no unit.
Unitless.
Right. So you will have to you're going to have to relate these two orders. So how do you know what is the angle? Now usually, and I'm going to go ahead and pull up the screen again, right? Usually what this looks like, you have this incoming light, right? It goes through the different slits, right? And then what will happen is that you will have a central fringe, and this is all one color. And let's see if I can, let's use circles to indicate that it's just one color. Then on either side of it, you will have a series of light and dark. And I'm going to go ahead and do this. I'm going to fill it in. So this will be darkness. Then you will have in the next light band the different wavelengths separated. So you won't see it as one uniform color at the central one. You see them in their different wavelengths. And I'm using the squiggles to represent each particular wavelength, like a particular wavelength. So this will be order 1, order 2, order 3, 1, 2, 3. So here is the line of incidence generally representing the axis. And then you would have observed on either side of this central, you will see that there is a bending, and we measure the bending by angle. And let's use theta 1 for the first order, right? And then for the second order, it's measured again with respect to the central line, and we use theta 2 for the second order. So notice that theta 1 on either side should be equal. So usually depending on the protractor that is on the grating, you have different options. You will find the difference between the central, which is usually at 90, and the value that is for the whether the left or right, right? And you would then say, for instance, you found that here is at 90, this one say record at 107, and say for this one would record at 80, let's do 82, right? So then the difference between 90 and 107 would be 17 degrees. Whereas the difference between 82, no, not 82, sorry, 72. Difference between 72 and the 90 would be about 18 degrees, right? So then what you would have done in order to figure out what theta 1 would be, it would be half of the sum of the two. That is it, depending on how the grating is. So you would find that this would have been, say, 17.5 degrees. The next option to determine what theta 1 would be to find half of the difference between the two values, which would be the 107 degrees, sorry, minus the 72 degrees. And in this case, you would get 17.5 degrees, same value, right? So those are the two options in order to figure it out. So either you find the differences you find the difference between the value and the central fringe, as well as the difference for the order on the other side and the central fringe, and then sum those differences divided by 2 as you find in the average, or you simply find the difference between the two angles and then divide that by 2. So those are your options that are available.
This is to get what?
This is to get the angle for the particular order, for that particular color in that particular order.
So we're going to use the order from the table, first order, second order.
That's correct. So going back to the table now, right? That was just a quick explanation. Notice for the first order on the right, you would have seen 166 degrees. And for the first order on the left is 152 degrees, which tells you that this table does not have 90 as the central, or where the central is lined up. It's somewhere in between. So you couldn't use, in that case, the very first relationship I gave you. What instead you would have to use is the second one. You would have to find the differences between the two angles and divide it by 2. So going back to it, you'll see, for instance, this is 166 degrees on the right, and 152 on the left. So then you would have found the difference between the 166 and the 152, which is about 14 degrees, and divide that by 2, that's about 7 degrees, right? And so you would find that the angle for violet, the moderate intensity, the moderately intense violet, which has a wavelength of 405 degrees, would be 7 degrees. So clearly you're going to have in that table the wavelength. You would also have in that table the first order angle on the right. You would have the first order angle on the left. You would now also have a column which has the difference between them. You would have another column which the difference divided by half, and then you'd have the final column which would have sine of the angle, because you are at the end of the day going to be drawing sine of the angle versus wavelength. So at the very minimum, you must
repeat that.
Repeat what, Mr. Morgan?
After you said wavelength.
Okay, you're going to be drawing your wavelength versus sine of theta. So as a result, at the very minimum, you must have the wavelength value and sine theta. But because you're generating a report, you are providing the data that you use. So as a result, you have to incorporate your values that you are given, which is the angle on the right, the angle on the left, the difference between them, as well as half of the difference between them, because the difference between them is the difference of the angle of separation for the orders, but you want how it has bent from the central fringe. So as a result, you have to divide it by 2. Okay? Now, when you're doing sine theta, please do not put it on the angle because angle has degree as its unit, whereas sine theta is unitless. So, yeah, sorry, give me a second. So,
So me too must have the angle separate and then have sine theta in the next column.
right, so those will be in columns themselves, but you can have an overall heading, just like in this case. You can have an overall heading for the different angle calculations. Give me a second. Sorry about that. So they will have angle degree as their units, right? So you can have an overall heading as in this case where you have right angle slash degrees, and then underneath that you would have on first order on the right. No, you would have first order, then you would have on the right, on the left, then you would have the difference between them as well as the half of the difference. So those can fall under the overall angle slash degrees. But sine theta is unitless, so it cannot fall underneath this overall heading. It has to have its own total column heading and everything. Just like wavelength will have its own total column heading and all. Take note that the wavelength is in nanometers, so this is 4.05 times 10 to the minus 7 meters, which is the same as 405 times 10 to the minus 9 meters. So you can choose to use times 10 to the minus 7 where you put it in standard notation, which would be 4.05 times 10 to the minus 7 meters, or you use it as your 405 nanometers. Now, if it is that you had downloaded this before yesterday, you would have seen there was a mistake where nanometers was not placed there. So I have gone ahead and corrected it and put in the nanometer. So the new version that has been uploaded since yesterday has the nanometer. That's the only change. So if you have the old version, please remember to take note that that these values are in nanometers. So that's for the first table. You draw your first graph, and then you do your calculation, see if you can get a spacing value. The spacing value, you're gonna do error calculations on it because you're gonna do your uncertainty, and so that will tell you the range within which the values really should fall, or the amount of the degree to which you are not sure of the value itself. You're also going to determine the accuracy of the equation or the method itself. Remember, percentage relative error is what you use to determine how well the experiment performed. So you are going to compare the value that you calculated using this true value, D equals 300 lines per millimeter. It's not 300 lines per meter, but 300 lines per millimeter, which means you will have to figure out how many lines there are per meter and use that to compare it with the spacing value that you get. Now, be very, very careful when you're doing a gradient calculation to make sure that you write the times 10 to the minus 9 or the times 10 to the minus 7, depending on which notation you use, whether standard or the non-standard, where you use the 4 or 5 nanometers. If you don't put it in, you will make a mistake in your spacing calculation, and you will find yourself with error, and you're going to assume that you have a 3,000% error when you do the percentage relative error, when the truth is it really should have been 3%. It's just that you were wrong in how you used your prefixes. Okay. So then, of course, you're
is it better? You mind if we convert from like the beginning of the table?
If you convert what?
From the beginning of the table.
That's exactly what I was really driving at you to do.
Alright.
But then, of course, you're not restricted to it because nanometer is still metric. It's still representing it in meters. It's just that you put the prefix in words rather than in number. It's just that a lot of students forget the nano part, they forget to use the times 10 to the minus 9 in calculations. And so as a result, their final answer will be off by orders of to the minus 7 or 10 or 9 depending.
All right.
Okay. All right. Which is why I always say carry units every step of the way. That eliminates all issues or potential issues. Right. So as I was so then you would move on, you'd have your second table, but the second table would be for the second order, similarly completed as the first table. There we go. So it seems like you're all set for today. Any questions before I leave you up to go into your groups?
Basically, we go use as well before go use the equation and set the expectation and them something the same way.
Something their same way, Mr. Hodges.
Sorry. We use for the
Why does it sound like you're not infused, Mr. Hodges?
I am.
So yes, let's talk about your expectations then. So yes, you are going to be looking at your graph and your table, and you're going to have, before you even start to evaluate them. As a matter of fact, in the very first place, based on your equation and your background, you already have expectations as to what it is that you want to see or you should see. You already have determined that you should observe a positive relationship between the wavelength and the angles, and you would have looked at it and noticed just here in this case 166 between 166 to 152 and divide that by 2, that's already 7 degrees compared to 169 and 149. This is now going to be 20 degrees. 20 divided by 2, that's 10. So you can see that moving from violet all the way to yellow, you observe an increase in wavelength with increasing angle, right? So already you start to see this positive relationship which your table is already verifying. Now whether the relationship is proportional or not, you need to compare it with the sign. So that's when you would use your graph and look at it and then be able to see. Why are you shaking your head, Mr. Hodges?
Oh no, miss, I wasn't shaking my head. I was scratching my head. Sorry, I wasn't shaking my head. I was listening.
Okay. So you would be able to see if based on these, if your expectations are met, and then you would be able to discuss them. Now, I'm glad Mr. Hodges asked about the expectations and the discussion because I need to point out.
Oh, man, I'm going to answer the video.
Pardon me?
I lie.
Oh, that's not me, it's Mr. Morgan. Okay, I guess not. All right, so in terms of your discussions, right? A number of you are still wasting time. You're still telling me background information, defining the terms in your discussion. If you want to do any definitions, that's for your introduction. That's when you're providing that background information. And you don't waste time on those things either. You explain what these definitions actually mean or what it is or related to the concept itself. In your discussion, you shouldn't be defining anything or explaining anything and telling me what M represents versus what doesn't represent, right? Some of you are also giving information that the graph, that the tables were generated, and from these the graphs were plotted, and then once the graphs were plotted, gradients were calculated, and these gradient values were, and using the gradients, we then went ahead and found the calculated whatever else after. You are repeating in that case the calculation method, the method of evaluation. You are not supposed to be discussing that in your discussion. You repeat no method. Don't repeat the method that you use to carry out the experiment, or whoever used to carry out an experiment. It's already clearly put forward under methods. Do not repeat the apparatus that was used, that's already put forward under apparatus. Don't repeat that you calculated this and presented whatever you did, whatever graph generation. All of that is viewed under results. They can clearly see the steps of what you did in order to get these results. Right? So in your discussion though, what you're spending the time to do, which I've been trying to tell you from beginning, is explain what your results mean. Explain how they meet your expectations and why. When you develop something new, in that case, you would explain further how it can be used, or what then can be done, or why it works, and how else it could be improved, and all of those different things. But this is a simple experiment. You have Bactive, which was in your introduction, as to why it should work, and so now you use them to explain why it does. You were able to calculate the grading spacing because of the fact that there is a proportionality which was demonstrated in the graph. These sorts of things, you're going to explain why. When you present equations to justify or to support or your explanations, then you need to also define the terms in your equations. If they are defined somewhere else previously in the document, then you refer to it. So if you defined it in the results section, you see as defined in the results section, where the terms are as used as they have been defined in the results section. Or if you had defined them in the introduction, which you really shouldn't have, you refer to it. Wherever you've defined it, refer to it. Or if it is that they are used as is in the handout and already previously defined in the handout, then you can refer to them as they were used as defined in the handouts. And you state the name or the title of the handout.
Yes.
Yes,
As it relates to the discussion, can we state our answers in the discussion also once we're given some information about it? Let's find the spacing gradient so we can indicate that in the discussion or not.
Your results already has your uncertainty. What you explain in your you explain what that uncertainty means in your discussion. So you don't if you even quote the value, you cannot just quote it and leave it. You have to explain that this shows that the value that you calculated may not be absolute, but falls within a particular range, and so forth, right? And you may give reason as to why it is that it may not have been absolute. So that is, you don't just quote it. You have to explain it. And a lot of you also keep talking about systematic, and I have persons in the waiting room, give me a second. A lot of you keep talking about systematic and human.
And miss, even that, miss, because we're basically not doing the practical, miss, it's really hard for people to think of things. So I'm imagining doing the practical. I have to imagine what could be some stuff like that, miss. So that kind of give some reason why we can't give a proper me in this case.
I understand what you're saying, Mr. Hodges, and I agree that it is a limitation, right? But then in the event that you're not able to remember, that's why you have the extra time to focus on then finding out what are some of because these experiments are readily available on the internet. So you would have seen some of the limitations that are expected in carrying out these experiments. And then also, I do try to tell you, I mean, I quote it as a human error or so forth, right? But I do express some of the limitations. Is just that I don't classify it, which is what I expect of you. Don't classify it as human error or classify it as systematic error or random error. Those things are for you to learn to understand what type of errors they are. But when you are presenting your limitation, state the limitation itself. State the fact that temperature, there could have been temperature variations in the room that may, and this is not for the grating one, certainly. But for instance, if you were trying to determine the temperature of a tabletop, right, in an experiment, and then you were in a room where the same temperature was not controlled and maintained at a particular value, it would affect the temperature reading you would get for the table. So in that case, you wouldn't talk about systematic error with the room being a particular whatever or anything like that. You would explain that temperature variations in the room could have affected your ability to get any particular affected each individual result differently, which would then affect the total accuracy of the results and your ability to conclusively confirm the table's temperature, right? So you don't classify and just say random errors could have affected it, right? Each temperature variation at any given time can randomly affect the result that you get, as well as the fact that there is a temperature variation can create a systematic effect on the temperatures that you collect. So you classifying it as random or systematic can cause an issue because it could be a random effect at that particular time, right? So, but then you were taught the different types of errors or effects just for you to understand the differences in how they behave and how they affect.
Miss, go ahead. Sorry.
All right. Yeah. So according to the equation of the graph, we should not receive a y-intercept. Right.
Well, based on this one, you shouldn't. However, you are not going to force your line of fit to the 0, 0. You are simply going to let it fall wherever it may. You're going to draw the trend that you observe in your results and draw the line that seems to best fit it. And then if it is that it goes to 0, 0, great. If it doesn't, then it doesn't. You go ahead and explain. That's what your discussion is for.
All right, Miss. If you use the box method, you want the box on the graph?
Okay,
You want to show it?
you brought that up, Mr. Morgan. So
Wait there now.
I said, I'm glad you brought that up. Some
Okay.
of you have a habit of assuming that once it is that you're going to do your error propagation based on your gradient error, you're going to use the smallest subdivision. I told you from the beginning that you use the smallest subdivision method if your points fall within one subdivision away from the line of fit or on the line of fit. If it is that any point falls outside of one subdivision away, then you must use your box method. Your smallest subdivision method becomes irrelevant, or you would have to use a larger subdivision, and in that case you're trending towards the box method anyway. Okay,
Right.
that answer your question, Mr. Morgan.
Yes, so so you'd like us to show it then?
Rami?
Because I was wondering if you wanted to show it on the graph. Or
No. You mean the box method? Once you have
Yeah.
to do the box method, unfortunately, you have to show it. But then here's the thing though. You have the option of copying the same graph and presenting it otherwise. Copying it and doing it on the copy version of it. That way you have your provided unaltered graph which shows your results, and then
Right.
you also have one which shows your ability to calculate shows your method to calculate your uncertainty.
Okay.
All right, but then you can also change your subdivision, your smallest subdivision, but you wouldn't change it to be too big, because in that case you're already training to box method. So you don't have to do the extra tiny boxes. Okay. All right.
Okay.
So, ladies and gentlemen, I'm going to now assign it is now 9:10, 9:09 to be exact, on its way to 9:10. I'm going to check who I have here first, and then I'm going to Miss Rera. Are you still here? I see Miss Dixon.
Yes, miss, I'm here.
Okay, all right. So, Mr. Sterling, I see you. Mr. Hodges, I see you as well. Mr. Miller, I see you too, and Miss Barnes as well. Mr. Scott, I see you, and Mr. Wisdom. Mr. Wisdom, I don't see you. Okay, I see you now. Mr. Tom. Oh, yes, I do see you. And Mr. Chin, I see you. Mr. Humphrey, yes. Mr. Swaby. Oh, yes, for sure. Miss Salmon, yes. Mr. C. Thomas, yes, I see you as well. Mr. Blake, oh, okay, there we go. Mr. Johnson, yes, I see you. Mr. Morgan, I've heard you, but I don't see you. Oh, I think you had sent me a message, right? Is that correct, Mr. Morgan?
Yes, Mr. I had sent it
And then Mr.
from last week.
Right. Mr. Horn, yes, I see you, Mr. Well, I almost see you, Mr. Horn. There's so much light behind you. Mr. Davis. I don't see you, Mr. Davis. Yes, I see you now. Mr. O. Thomas. Oh, let me change over to the next side. Let's see if I see Mr. Thomas.
I'm here, miss.
Where? Oh, yes, I see you now. Miss Meek, are you still here?
Yes, miss.
Okay, thank you, Miss Meek. And then finally, I had Miss Rary already answered. Miss Dixon confirming that you're still here.
Yes, miss.
Okay. All right. So, ladies and gentlemen, please take a 2-minute mental break from my voice.
I didn't hear my name, miss.
Oh,
Never heard my name, either.
I didn't hear my name, miss.
Nine.
Mr. Adrian Lawrence, that's Mr. Matthew Brown.
How many?
And Mr. Swaby, I did call your name. So please take a mental break. I'm going to go ahead and assign you with partners. I'm going to open the rooms in the meantime as well, and then I'm going to tell you who you've been assigned to work with.
Miss, I didn't hear my name either.
Oh, Mr. Tulloch, no, I didn't call your name at all. Before I do so, though, is there any question? Okay, nice.
Oh, the blood.
You might want to mute that one, Mr.
What you eat?
Okay, all right. So you have been assigned. Let me tell you how your assignment is. Remember, you will do the evaluation based on the group number on the data on the X in the Excel file. So for group one, oh, and please remember, ladies and gentlemen, you are required to do your share of the work, right? So when you're working with a partner, please make sure that you provide adequate input, and also please make sure that both parties sign off on this before it is submitted, right? In the in the event that you don't get please give yourself, you know what, there's no in the event. Sorry, please give yourself some time to make sure that both parties have enough time to view it before you submit. All right, so for group one, we have Mr. Adili Sterling working with Mr. Kieran Hodges. Mr. Miller and Miss Barnes will work in group two, so that's Mr. Leroy Miller plus Miss Morgan Barnes for group two. For group three, we have Mr. Rajay Scott working with Mr. Joel Wisdom. So that's Mr. Rajay Scott working with Mr. Joel Wisdom. For group four, we have Mr. Javasi Tong. He'll be working with Mr. Yasan Chin. So Mr. Yasan Chin, you'll work with Mr. Javasi Tong for group four. For group five, that's Mr. Dominic Humphrey working with Mr. Damali Swaby. So I don't know what that is for. Oh, I see. You're happy about that assignment, Mr. Miller working with Miss Barnes. So, okay, Mr. Dominic Humphrey working with Mr. Damali Swaby for group five. And then for group six, we have Miss Tiffany Someone working with Mr. Curien Thomas. So group six has Miss Tiffany Someone working with Mr. Curien Thomas. For group seven, we have Mr. Josh Blake working with Mr. Jonathan Johnson. So group seven, Mr. Blake working with Mr. J. Johnson. And for group eight, we have Mr. Shamar Morgan working with Mr. Alwa Horn. So both Mr. Morgan and Mr. Horn will work as group eight. For group nine, we have Mr. Javier Davis working with Mr. Olandre Thomas. So Mr. Davis and Mr. Thomas, that is, will work in group nine, in room 9. For group 10, we have Miss Deidre Meek working with Mr. Adrian Lawrence. So Miss Deidre Meek working with Mr. Adrian Lawrence as group 10. In group 11, which will be working in room 11, that's Mr. Matthew Brown with Mr. Jean-Marc Tulloch. So Mr. Brown and Mr. Tulloch, group 11. And then finally, our two participants, additional participants, Miss Rary and Miss Dixon, you will both be working in room 12 as group 12. That means you'll evaluate data 12. However, for Miss Rary and Miss Dixon,